Hi there, this is Paul Edwards with Denmark Company, and today I'm going to be talking about the use of Flaco citric acid ready to use on a hand spray system. But before I do that, I'd like to go over some of the basic important elements of safety. First of all, it's always important to remember to wear latex gloves whenever you're handling chemicals, and also you need to know what safety glasses are needed and so forth. So you definitely want to have nitrile or latex gloves, and you also want to have safety glasses as well. So that's one of the safety first elements that we need to consider. The second thing you need to remember is that if you have an exposed chemistry in your facility, you want to go on and use a cover on that, and that's what this is right here. It's a cover for this vessel here, which is the tank that your antimicrobial goes into. You also want to make sure that that you have anytime you do testing, you want to test with water. So that's water right there that you're looking at, and you can see that it has a level in it right now that it's approximately 5 gallons of water. And then the last thing that you see there at the very bottom is your label of the chemistry that you're using. Right now what we're going to be using is ready to use citric acid 2%. And by the way, at Denmark Company we market a non-GMO fermentation of the citric acid. So it would be a product that can go on products that are USDA certified organic. So this is an organic citric acid that's eligible for USDA certified organic on products that are USDA certified organic. Okay, so right now what I'm doing is I'm working with a tank that is square tank in nature, and then you have an option that you can go on and utilize a oval tank there. You see how that tank is round and then straight up. It's kind of like almost an oval shape, but a tubular shape for sure. And that's also available through Denmark, where you have this configuration in a tank such as this one right here, which that's about approximately 15-gallon tank, or this one right here is approximately the same amount of gallon. Each might be 20 gallons maximum capacity. And so now what we'll do is we're going to go on and move on to the system itself. So I'm going to put you on hold. Okay, now talk a little bit about the pump, and basically what we've accomplished here is we have a tank that's feeding this pump as a flooded suction, meaning that the water is entering the pump in such a way that it's over the inlet port, the level of the water, or in this case it would be citric acid 2%, is over the level of the volume here. So basically what happens is when you have it over this level here, the volume of water is up in this level here. It feeds into this line right here as a flooded suction. The pump then takes the chemistry with its impeller. This is a corrosive resistant impeller, and it runs it right up into this line, which the line itself goes to a hand wand. And you see this little, it's not fully open, and the reason why is because I calibrated the outlet of that pump to the hand wand, and I'm using that ball valve to act as a flow control device. Okay, so that's the purpose of that there. Okay. So now we're going to go to this next section. Okay, this is Paul. I'm back with you. Now what I'm going to do is talk about some other techniques that I'm using here today. First of all, we have this hand wand or trigger gun, and basically what it has is a tip at the very end of it. Okay, you see that, and it goes on and off with the hand trigger here. It's a trigger gun, and then this nozzle will spray a certain volume. So as you saw that pump, it had that ball valve cracked a certain way. Between that and this nozzle tip, which is spec'd out as a 6530, and I'll have to explain to you on a different day what that means. But what I did was I took this hand wand, I timed it with my phone, which has a clock stopwatch on it, and then I took this 2 gallon sprayer here, and right here is the 1 gallon mark right there. So I went on and filled this up. Notice that this has our label too, Flaco, citric acid, or acidified sodium chloride, whichever you're using. But we have those labels for your pump up sprayers and also for your tanks. So please give us a call, let us get that set up for you, okay? So basically what I did was I used my stopwatch. I opened this up by pushing the trigger down, and I ran it for 60 seconds, which is 1 minute, to find out what my flow rate was. And I was just above 1 gallon per minute. I was about 1.2 gallons per minute, okay? Now, that right there, that step that I just did, calibrated the suction of the pump, the flow rate of the pump. I calibrated it with this over 1 minute, and so that told me that when it's turned on, what that flow rate would be based on seconds. Okay, so 1 second is so many ounces, 2 seconds is so many ounces. So basically, if I'm operating at 1.5 gallons per minute, you take that 1.5 gallons per minute and you divide that by 60 seconds in a minute, that would tell you exactly how many ounces per second are coming out of this system, and it should match up to your scientific and supporting documentation. Now I'll explain a little bit of that here in a second. One other thing that I want to show you is this foot pedal. Okay, so the foot pedal right here, this is the power to my pump that's pushing the chemistry to my hand wand or handgun. This is where that pump is connected to right there, okay? And this cord right here is connected to power. So I have a foot pedal that controls my power on and off to the pump. Now here's what's interesting about that. I can have that foot pedal right next to my hand wand, right? And I can have a cord all the way. It could be 100 feet away, it could be 200 feet away, it could be 300 feet, whatever distance you want, minus the capacity of your pump. Now remember, you don't want to go too far if your pump isn't sized to push, your chemistry a distance of, 100 or 200, 300 feet. If it's not sized to do that, then don't ask it to do that, by setting an extension cord all the way out there, okay? So basically understand the capacity of your pump. Basically I would say that this configuration is for a small operation, so keeping that in mind, it's not uncommon to find the pump located approximately 50 to 60 feet away from your hand wand. So basically what happens, you have your foot pedal that operates the power on, power off to your chemical by just depressing it. And then you also have the trigger sprayer that's on and off. So you'll find me pressing my foot onto the first, and then I'll open this on and I'll do off, and I'll do this on and do off. The reason why I did that is because two things. First of all, I'm a real big believer in safety first. So I think that your foot should tell your pump when to be on, okay, especially in a small area confinement. Now other people may not believe me on that, and that's okay. I'm just saying that the way I've configured the system, I've got a foot pedal that tells power on, power off to the pump that's pushing the chemical all the way from the tank to your hand wand, okay? And that is controlling the amount of pressure in the line. Okay, by turning your pump off, you're controlling the pressure in the line. By turning your pump on, you're increasing the pressure in the line. Now, we're not going to have a lot of pressure with this size pump that we have, but if you develop a leak, or if you develop somehow a disconnection somewhere, or you have just something that could happen randomly that would affect your willingness to turn off the pump, you can do that with your foot pedal. And the other thing I like about this foot pedal is, unless I'm pushing down the foot pedal, there is no power. So you can bypass that by just saying, look, I want the power to the pump on all the time. I don't want my foot turning it on or off. But as a fail-safe, I'm just saying that with your pedal, you're telling it, do not start feeding my hand one until my foot is telling you to do that. So that's the way that's configured, okay? So I hope that answered your question on calibration and foot control of your hand one. Okay, now we're at supporting documentation, okay? I have two studies that I'm going to refer to for the supporting documentation to give you an idea of what I do to validate a flow rate based on microbial reduction, okay? I have a study here by the U.S. Meat Research Center, part of the USDA, that is the Clay Center, Nebraska Research Center. I've had the pleasure of working with those people in the past. They're very intelligent, they're very capable, and they know what they're doing, and they're out to help you, the processor, with all the information you need and all the validation support that you need. Okay, in this case, we're looking at a citric acid, lactic acid, and acetic acid validation study. Now, the important thing about this validation study, and you can see right there, you see where it talks about the 1%, the 2%, and the 3%, excuse me, 1%, 3%, 5% citric acid. That is what the validation information that we're using. Now, what they're saying here is that when they did the validation study, that they were working with a certain PSI, they were working with a certain liters per minute, and a certain distance, and a certain temperature. And I just want to give you my opinion based on some of the new validation requirements in the plant. These are verification, USDA verification. Okay, in a USDA verification in the plant, you got to think of things as two different approaches to the facts. Okay, first, you have approaches to the facts that have to do with maintenance. Okay, so when you start looking at pressure, and you start looking at distance, and you start looking at temperature, that right there, from my personal experience, is information that is intended for the maintenance department. Okay, and they are not critical control points for the antimicrobial intervention. Okay, I'm not going to go into a lot of details, but I'm just saying that for the purpose of the prerequisite program, whether it's attached or not to the HACCP plan, there are going to be some things that are strictly maintenance, and they are not accountable to the HACCP plan. And there will be other things that are strictly quality control elements that are prerequisite programs that were intended for the quality control to assure microbial reduction, and that is a prerequisite program that would be attached to your HACCP plan. Okay, so there's a big difference between maintenance prerequisite programs and the prerequisite programs for QA that has everything to do with food safety. Okay, so in this case, the issues that we are going to be dealing with on QA prerequisite programs to affect your HACCP plan is the 1% citric acid, the 3% citric acid, and the 5% citric acid. Okay, and for the purpose of this discussion and this supporting video, is I'm just basically saying is that we're flowing at 1.27 gallons per minute out of one nozzle in this study from the animal health science research. So those are the very important points that you have to understand when you talk about that study right there. Is you have HACCP plan important items. And in this case, for that study right there, it's the 1%, the 3%, and the 5% citric acid. And the fact that it was flowing at 1.27 gallons per minute. And the final fact is that when they sprayed these products with this chemistry, they only did it for a second. They didn't go and they didn't have a spray rate of 1.27 gallons per minute and kept it on the part, spraying on it for 5 or 6 seconds. It was only for a second that they sprayed the parts. This is a fan type design on this particular nozzle that they use in the study. It's a fan type. And so basically what happens is it's, as a fan, it's spraying like this, and it's an oscillating fan like this, so it's only doing this for a second, but there's so much volume that's being applied on the surface for that given second. So that's what we're working with there. I've got another study here that is done by Penn State University and a graduate student. And in that particular study, once again, we're dealing with citric acid because that's a chemistry that we're talking about right now. And in that study, once again, we are looking at specific percentage of concentrations. And in that case, the percentage of concentration of the citric acid is 1%, 2%, 5%. Okay? So those are very important points that I want to make. And in the case of the Penn State study that I'm referring to, what we're looking at is we're looking at a nozzle volume of, let me get that, go to that section right there. Very similar to the USDA Research Center's nozzle volume, which is 0.73 gallons per minute. Okay, so it's less than 1 gallon per minute. I also looked at a counter study that basically we went with 0.73 gallons per minute in a nozzle specification that was listed in the Penn State study. But also what I did was I took the same volume, well actually volume is determined by pressure and orifice size. And so basically what I did was I took a look at the numbers on the orifice size and the pressure, and I found that once again this other nozzle specification with the same orifice size, the same angle, had at the same pressure, which is 40 psi, had a similar volume to that of the USDA study, which was approximately 2 gallons per minute. So we've got now a study and support information for 0.73 gallons per minute. We have one of 1.2 gallons per minute, and we have another one of 2 gallons per minute. And when I validated my flow rate out of my hand wand here, I validated in my facility, which is considered an implant verification, I validated that it was flowing at greater than 1.2 gallons per minute. And in both these studies, the USDA and the Penn State study, basically what they were doing was they were taking a particular area and they were spraying it in a wave motion, and depending on how many times they went up and down, that would be the multiplying factor of volume that's been placed on that by going up and down. But and whenever you have this up and down motion of one nozzle that it's oscillating, like the USDA study, that if you're working with 5 seconds and you're working like 1, 2, 3, 4, 5. So you basically have 5 sprays simulating similarity to 5 nozzles because it's oscillating back and forth. On the other study, that's the Penn State study, once again you have that. Now, Penn State study was on a carcass, whereas the USDA study was on trim. The point I'm trying to make here is that in both studies, what we're seeing is about a 1 to maybe 2 second application to the surface, and that's it. Okay, they didn't stay there focused in one spot for 30 seconds, where you take that one spot and you have to multiply it by 30 times to determine what the volume is, because when you have the volume per second, then you have to take that volume per second and multiply it by 30 times. If you've got 30 nozzles that are all hitting that one spot at the same time, or if you have an oscillating system that keeps going over that same spot, and within 30 seconds they've hit that same spot 30 times. So what I'm saying is, in an implant verification, it could get that complex with where they're actually trying to get the exact volume from you. I really don't think that they're going that direction with their implant verifications, but realize the Danmark company can help you decipher these studies right here so that you know what the actual second flow rate is, and you can see that in your plant you replicate it. Okay, so that's pretty much it on that. I'm going to go on and demonstrate the hand wand here next. Okay, this is Paul Edwards. I'm back. We've gotten to the final excuse me, I'm sorry, I didn't mean to cough all over the place. I'm going to actually grab a water because I think I got a crick in my mouth or something. I don't know what it is. Okay, so I got my water here. I'm going to have a little drink there. So basically what I have is I have a containment basin here. That's what I want to call it. I got my hand wand and I got my pedal here, okay? And basically what I want to do is I want to demonstrate for you what this flow rate looks like at 1 second, okay? And then kind of give you an idea what it looks like at 2 seconds and stuff like this. Now I want you to think of this as a maybe a whole muscle product or some large trim or something like this. So this is an area here that you've got laid out, this meat, and what you're going to do is you're going to spray it and then you're going to flip it over, okay? And so I'm going to take my water bottle here and I'm going to make it a piece of trim. I'm going to throw it here in the middle. Okay, and I got my hand wand here, or handgun, and then I got my motor for my pump, and it's on a pedal. It's controlled by a pedal. You hear that in the background? That's the pump. Okay, it's feeding power and solution to my hand wand. Okay, and I'm actually a right-handed, but for this I'm gonna use my left hand so that I can show you basically what I'm doing. So I've got both my hands free here, and I've got this pedal, and so I'm gonna go on and fire up the pump, and then I'm gonna go on and depress this hand wand, and then I'm gonna spray that spray bottom, give an idea of what we're talking about here. Okay, did you see that? That's where, like I said, we're running at about 1.5 gallons per minute through this nozzle based on the pump size that I have and the throttling that I did with the ball valve. But did you see how I got that on there? Now what I'm going to do is I'm going to turn it over like this. This is water I'm messing with, so always test your products with water. Okay, do all your calibrations, all your validations, all of that should be done with water in your tank, never with chemistry, okay? And if you are working with the chemistry, of course what you want to do is you want to wear latex gloves or nitrile gloves. You want safety glasses. You want to make sure that your arms are covered, because we are dealing with citric acid, okay? And it's 2%, but at 2% your pH is about 2 pH, and so, you know, although it's not as aggressive as some of the chemistries that I found out there that are at our 1 pH or below. We don't have that case here. It's still good to know what your pH is and protect your employees from anything like that, okay? So I'm going to press my pedal again. Here I go. Okay, that was 2 times I went. Did you see that? Now, I've sprayed this approximately 3 seconds worth of spray, or 3 times I've run this spray in there. Okay, what I want you to do is I want you to get an idea of what we're talking about here, okay? This is 4 ounces right here at this level here. I'm going to take this container here. I'm going to put as much of this fluid I can without dripping it all over the place. Kind of give you an idea of what I applied, okay? So once again, let's pretend that I had a couple of trimmings here. So this could right here be about 6 pounds worth of trimming. I sprayed it one side, turned it around, sprayed the other side. Let's say that I used a total of 3 passes to get this area here sprayed, okay? In those 3 passes with that flow rate, I only applied 6 ounces, okay? And that 6 ounces is basically what the USDA did in their study, and that fellow, the people did at Penn State, is that's the volume they were working with, okay? Now these are trimmings here that we're looking at. You know, same thing with the carcass. If you have the carcass, that flow rate that you just saw would be acceptable flow rate based on the study that that I've looked at. Because I did the nozzle volume specifications, okay? These nozzle specifications are available through Spray System. So what I do is I take a look at the angle, I'll look at the orifice size, and I look at the pressure, and then I actually know what an application flow rate is, okay? And then I know that that application flow rate is what's making its spray onto the surface of the meat. And that's what's important, okay? It's not the distance between the nozzle and this spot right here. That's not an issue. That right there is only for maintenance. What's an issue is what was the volume applied to that part of the meat. When USDA and this other Penn State University, they did their study, to them, because of the distance between the nozzle and the part, they went with a higher flow rate, and both those 2 studies support each other with the microbial outcome. Because what we're basically seeing in both these studies, and I'm going to just kind of give you some numbers here, and then I'm going to end this because we only have so much time and attention spans that we deal with here, right? Okay, so what we're looking at basically in the E. coli study, what we saw here is we saw about 1 to 2 log reductions in E. coli organisms based on the use of citric acid, okay? And that's a very, very important outcome, because basically what happens is that this application here at your plant, this application is part of a multi-hurdle process that originated in the kill plant and then moved all the way from the kill plant to your facility. And so that micro reduction accumulate. And according to this study by the USDA researchers, they found anywhere from a 1 to 4 log reduction based on the chemistry that they were looking at. And remember, they were looking at a 1% to 3%, 5% on lactic acid, acetic acid, citric acid. And what we were more interested in was the citric acid, because citric acid applies to us. So that's the most important part on that particular study. Okay, from the perspective of looking at microbial reductions in concentrations, I can tell you this. Okay, at a 5% citric acid, lactic acid, and acetic acid at 5%, they all had greater than 4 log reduction. Okay, so that's a pretty good log reduction. At lactic acid, citric acid, acetic acid, at a 3%, also once again did real well, about a 4 log reduction. And then when you get down to the 1% lactic acid, 1% citric acid, 1% acetic acid in the USDA Animal Research Center study, we're looking at about a 2 log reduction. So that's pretty darn good. For being part of a multi-hurdle intervention, that's pretty good. Okay, now on the Penn State study, what we're seeing there, where they actually not only looked at E. coli, but they looked at Salmonella and Campylobacter. What they did was they found that at Salmonella, what they saw there was about a 3 log reduction at 2%. They saw about a 0.7 log reduction. Excuse me. I'm sorry. Let me rephrase myself. Okay, in a Campylobacter, let me start there. Campylobacter, we saw at 2% citric acid, we saw a 4.69% reduction. In Salmonella typhimurium, we saw a 3.58 log reduction with citric acid at this flow rate that we're working with right now. And then at E. coli 0157H7, they saw a 3.6 log reduction with a 2% citric acid. Now, what's interesting about this finding is that this is the reason why I think that this is really unique, is that I'm finding that between a 2% solution and a 5% solution, the increase reduction is not significant enough for an increased cost related to being a 5% solution. So what I'm saying is, by shooting for the middle, by going with the 2% ready to use, you're getting a very good and significant reduction based on the study results that Penn State found. Okay, and so that's an important finding. Now, I'm not going to be talking about the other antimicrobials that Penn State studied, primarily because what I'm talking to you about today is the ready to use chemistry of citric acid 2%. And I want to finish up by making just one more point, and I'm going to let you go because I know that you guys are real busy. Got a little water drink there. Okay, here's something you really need to know about this chemistry and why we have a 2% ready to use. The reason why we create a 2% ready to use, okay, and do not take these terms as derogatory. I don't mean to do that, okay. I use terms like no-brainer, foolproof, easy to apply or ready to apply, easy to control, easy. And the reason why is you're just taking it out of the 5-gallon bucket, pouring it in directly into the tank, and it's ready to go. Okay? This product comes with its certificate of analysis of the 2%. So you know that it's certified 2% by weight chemistry, which is exactly what this study was done at 2%. There's not a huge difference between 2% of weight and 2% of volume. I've looked at that number before. I have supporting documentation. When you look at 2% by volume and when you look at 2% by weight, the pH is about the same in both those, okay? So don't get stuck on 2% by volume or 2% by weight. We're looking at the pH here on that, and basically that pH doesn't change at all significantly, okay? So the key word there is significantly. It does not change significantly, okay? Very small, subtle difference in the pH from those two, okay? We've got great microbial reduction. I'm here to help you with any questions you have. We appreciate your business. This equipment is available at a very low price. And we have certain programs available where we actually provide you the equipment on loan at no additional cost, as long as you're buying chemistry from Danmark Company. We don't want to treat anybody different from the other. We want to make that available for all our customers if they're interested in there, okay? But if you buy this equipment and you run other people's chemistry on it, then that's your baby. You bought the equipment, so you can do that. But if you're running our chemistry and you're borrowing on loan our equipment, you can only use our chemistry through it, okay? I think that's a fair business relationship. I want to thank you for taking the time to listen to this, and please email any questions you have to Paul Edwards at danmarco1@msn.com. That's DANMARCO, the number 1 at msn.com. Our website is www.danmarco.net. And you can find some very good, very valuable information on our website. Thank you.